Here is an interesting question that came up in the IIT JEE Advanced. So this is a circuit question, and the question is asking us to find the current through the battery. So this is a 12-volt battery. You want the current through this battery. Let us say it is I. Okay. You can see that this is a nice symmetric circuit. This is 2 ohms, that is 2 ohms, this is 4 ohms, that is 4 ohms. Okay. So this current I that comes in will split up as I1, I2. And maybe it goes this way, we don't know. Let us say that in that branch it is I3 and in this branch it is I4. Now they will add up to come out like this. But whatever comes out here is the one that is going there. So this current must be I. Okay. Now, if I use these different variables, I'll also get some more variables there, right? And try to solve it becomes really messy. So we use the fact that this is a symmetric circuit to simplify matters. And while doing that, Sethu asked me a very interesting question. So Sethu's doubt was, Kirchhoff's current law just tells us that I1 plus I2 must be I and I3 plus I4 must be I. But if I use all different current variables and try and solve, the calculations becomes very hard. So we say symmetry and then we say I3 must be equal to I1, I4 must be equal to I2. But why does symmetry imply that, no? For example, you can argue 3 plus 7 is equal to 10. And you can argue 6 plus 4 is equal to 10. There are so many ways in which it can add up to 10. So why should it be that I1 must be equal to I3 and I2 must be equal to I4? I know that people say symmetry implies this, but isn't there some proof for it? Is there a reason or proof? Yes, there is a very, very good reason. And the proof for this is based on 2 important circuit principles. I explained these 2 principles to Sethu. I'm going to show that to you. The first important principle is the reversibility of current. Now, this principle does not require a symmetric circuit. Okay, so look at this circuit. Is it symmetric? This is 2 ohms, that is 5 ohms, 4 ohms, 7 ohms, clearly not symmetric. Okay, now let us say that this current is 9 amperes. Then what is coming out must be 9 amperes. Well, that is obvious, right? Because whatever enters this big junction must get out. So these 2 must be equal. Now, let us say that it splits up as 4 amperes and something else here. We don't care. Okay, so this is 4 amperes. And this is 5 amperes, and let us say that is 2 amperes. I am just making this up, okay? Now, the reversibility of current principle tells us that if you reverse the current, instead of sending the current like this and it going out that way, suppose I reverse the current at the entry and exit points, right? So I make this 9 amperes, this is coming out 9 amperes, then what will happen is all these currents will simply reverse. So here 4 amperes like that will become 4 amperes in the opposite direction. It will still be 4 amperes, but in the opposite direction. Similarly, 5 amperes here will become 5 amperes like this. And 2 amperes like this will become 2 amperes like this. So what is happening? Every current in this circuit will just simply reverse its direction. Same magnitude, reverse direction. Entry and exit, we reverse the direction of the current. So everywhere the current simply reverses its direction. Magnitude of that branch, the current will remain the same. 4 amperes like that will become 4 amperes like this. The direction reverses because entry, exit, the direction is reversed. That's all. So this is called the reversibility of current principle. Very important principle. Okay. Let us now look at the second principle. The second circuit principle, an even more important principle, is called the uniqueness theorem. So if you take a circuit like this, okay, linear circuit consisting, let's say, of a bunch of resistors, I'm telling you that the entry point and the exit points, the currents are 9 amperes. Well, entry and exit, the currents must be the same. So I'm telling you it is 9 amperes. Once I specify that, then this current I1, this current I2, this current I3 is automatically fixed. There is only one answer for I1, I2 and I3. Once I fix the boundary values. Given the boundary conditions, the current in each resistor has a unique value. Okay, this is called uniqueness theorem. Uniqueness theorem. Now these 2 principles, right? These 2 current principles, do they require a symmetric circuit? No. Okay, these 2 circuit principles don't require symmetry. These 2 are general principles, valid for any kind of circuit. But when we use these in combination with a symmetric circuit, something very interesting happens, and we can use that to answer Sethu's question. Let us see. Let us now look at Sethu's doubt, right? Sethu's doubt is, in a symmetric circuit like this, why should we say that I3 must be equal to I1 and I4 must be equal to I2? I'm going to show you how by combining reversibility principle and uniqueness theorem, we can prove that I3 must be equal to I1 and I4 must be equal to I2 for a symmetric circuit. Okay? So we're going to use symmetry in combination with these two principles. How do we do that? Well, we actually don't need the battery. I just need this current and that current. So I'll remove the battery so that we can think a little more clearly. You can keep the battery if you want, but I'm going to remove the battery. So I'm going to just say current I is coming in, current I is going out. And I'm going to use the reversibility principle and uniqueness theorem. First of all, what I'm going to do is, I'm going to take a copy of this here. And I'm going to turn this around, flip this around. So what will happen if I flip this around? Well, if I flip this around, this I will come here, this I3 will go there, I4 will go here, I1 and I2 will go there. So all you have to do is to take this and flip it around. So notice, when I flip it around, I've taken this and flipped it around. Nothing has happened. I've just taken it this way and I've turned it around. I've not used any principle, I've just turned it around. But because it's a symmetric circuit, when you turn it around, suppose this was 2 and that was 3. When I flip it around, this will be 3 and that will be 2. But it is symmetric. This is also 2, that is also 2. When you flip it around, it looks exactly the same. It looks exactly the same. Right? Nothing has changed. It looks exactly the same. Okay. Now let us think. So this is a nice symmetric circuit. Right? I have flipped it around. And what I have done here is a flipped circuit. But the flipped circuit looks exactly like that, except this current I is coming in here and going out there. Now it is coming there and coming here. But what will happen if I look at this original circuit? I'm not flipping it, I'm keeping the original circuit. And suppose I just simply reverse the current. I know what is going to happen inside, right? If this is I and that is I, and I reverse the current, using the reversibility principle, I know what is going to happen. Please notice, this circuit looks like this, but this is the flipped circuit, that is the original circuit. I have not flipped that, right? I have kept it as it is, right? I only flipped this. To show, I'll go back and show this to you. So remember, I had bought a copy. I took this, I made a copy. This exact copy. This is the original. Now I have taken this and I have flipped it. It looks like that because it's symmetric. That is the problem. But this is a flipped version. So this is the flipped circuit. Whereas that is not flipped, that is the original. Now what I'm going to do is I'm going to take these currents and I'm going to reverse the currents. In the original circuit, I have reversed the currents. But reversibility principle says when you reverse the current, this current will be I3, except it will be in the opposite direction, I4 in the opposite direction. So just the directions have got turned around. That's all? No, this also will turn around, right? This is no longer I1 like this. It's going to be I1 this way and this is going to be I2 this way. That's all. So all the current directions have reversed. So this is current reversed. But it's the original circuit, current reversed. Now, when I take the original circuit and reverse the current, this is how it looks. When I take the original circuit and flip it, this is how it looks. Let us look at these two. Because it's symmetric, you can see that this 2 ohms is actually that 2 ohms because it got flipped. But this 2 ohms and this 2 ohms, they look the same because it's symmetric. This is 2, that is 2. When that 2 comes here, this is how it looks. Notice these two circuits, they look exactly the same. They look exactly the same. 2, 2, 4, 4, 1, 1, 2, 2, everything is same. Except you have I1, I2. Here you have I3, I4. Wait a minute. If the circuits look identical and the boundary conditions are the same, what does uniqueness theorem tell us? Uniqueness theorem says that the boundary conditions are the same. The current in each resistor has a unique value. So the current must be the same. Whereas now, same boundary conditions, I've got different currents. That's not possible. So I3 must be equal to I1, I4 must be equal to I2. I1 must be equal to I3. Well, I3 is equal to I1 means the same. I2 must be equal to I4. So what have we shown? I3 must be equal to I1 and I4 must be equal to I2. Proved. So we have proved right? We have answered Sethu's doubt. Why should symmetry mean these two are equal, right? Why should I3 be equal to I1? Because when you flip it and when you reverse the current, they cannot be different. Because the circuit is symmetric, it looks exactly the same. And if it looks exactly the same, that means I3 must be I1, I4 must be I2. So that means I3 must be I1, I4 must be I2. That's why for symmetric circuits, you can quickly conclude that these currents must be equal. Okay, so using this, how do we solve? Well, so it reduces the number of variables, so you can use that to solve. Let us understand how to solve a question like this. So how do we use symmetry to solve a question like this? Let us understand that. Now this is I1, this is I2, that is I1, this is I2. Okay. Now if I wanted to use symmetry to solve this question, I still need to figure out what is this current. So let me say that this current is P. Okay. That means this current will be I1 minus P. I1 minus P. Okay. Now this current is P. It will come down. This is I2. So that means this current here will be I2 plus P. I2 plus P. Okay. And if you come here, I2 plus P comes here. This is I2. So that means there must be a current P going this way. Hey, there is a P going here and a P going there. So now this P comes up here, joins up with that. I1 minus P plus P is I1. That goes that way. So perfect. We have got Kirchhoff's current law all figured out. How many variables are there? 3 variables. Right? I1, I2, P. Now you can say, wait. What about I? I is I1 plus I2, no? So there are 3 variables, 3 unknowns. So I need 3 equations to solve. And if I solve and I find I1 and I2, I can figure out what is I. Remember, the question is to find I. How will I write the 3 equations? One equation is to write for this loop. So I'll write the equations. So you can write 2I1. Right, I'm starting here. And then this is 2 times I1, right? 2 times I1 minus P. And that is 2I1 again. So that is the potential drop from here to there. That must be equal to this potential drop, which is 12. Or you can write minus 12 equal to 0, but we can write it like this. So I'm writing the potential drop like this, and that is equal to potential drop 12. This is one equation, first equation. What about the second equation? I can go like this, right? So for the second equation, I'm going like this. 4I2 plus 4 times I2 plus P. 4 times I2 plus P plus 4 times I2. 4 times I2. And that must be equal to this potential drop, which is 12. But with 2 equations, 3 variables, I can't solve. So I need a third equation. Now the third equation, you can go like this, you can go like this, you can choose any loop. There are so many loops. Okay. So we chose one big loop and we chose another big loop. So we could choose this loop or we could choose this loop. It's our choice. Okay. By the way, all the other things will be dependent. So suppose I choose this loop. What will happen? 2I1 plus P into 1, right? So plus P. And this, if I go this way, it will be minus 4I2. Minus 4I2 equal to 0. I am not solving. You can see really messy. But 3 equations, 3 variables, you can simplify, you can solve. So you can solve this. Okay, solve this. And you will get I1, I2 and P. And the answer is I equal to I1 plus I2. You can do this. What a pain, no? Lot of work. It is definitely easier than saying I1, I2, I3, I4. That will be lots of variables and really messy. But still 3 variables, 3 equations also is too difficult. Now, I have come up with a very interesting theorem which I call as the extended Wheatstone's theorem. It's like Wheatstone's principle, but this is not a Wheatstone's bridge. You see, this has that extra pieces here, right? It has, you can think of it like a bridge, but then that is going somewhere, there is one more branch, all that. So you can do this very nicely if you know the extended Wheatstone's theorem. I'm going to explain that to you. I'll use it. I won't prove it, but I will use this. Suppose I have a circuit like this. R1, R2, R3, R4, R5, R6. Here there is a bridge connecting here, X, and that is Y. X and Y can be different. It's not even symmetric. Okay. It's connected, let's say, to a battery. Now, what is very interesting, here is a condition. If R1 by R2 is equal to R3 by R4 is equal to R5 by R6, and I prove this by using uniqueness theorem, but right now I won't do that. Okay, then you don't really care about X and Y. So then X and Y are irrelevant. You can remove them, you can change the value, you can say X is 1 ohm, Y is 5 ohms, you can make X as 7 ohms, make Y as 2 ohms, it doesn't matter. You can make X 0, Y 0, you can make X infinity, Y infinity, it doesn't matter. X and Y are absolutely irrelevant as the current through them is always 0. So this current is 0, this current is 0. Notice that we got P this way and P that way because actually that P was 0. You can reverse everything, you will say that is P and this is going up P, but the P turns out to be 0, so it's really irrelevant. Okay, so in this case, if this theorem is true, it doesn't even have to be a symmetric circuit. In this case, this and this really don't matter. So how will I use that here? Because you see this I can do whatever I want with that 1 ohm. I can change that 1 to 10 ohms. It won't matter, it's irrelevant. The current through it is anyway 0. Okay, 2 by 4 equal to 2 by 4 equal to 2 by 4. For symmetry, this doesn't have to be 4. But if you want Wheatstone's, extended Wheatstone's principle to hold, then 2 by 4, 2 by 4, 2 by 4. It doesn't all have to be the same. It has to be the same ratio. Well, here they are all the same numbers, so it will be the same ratio. Since 2 by 4 here is equal to 2 by 4 is equal to 2 by 4, it doesn't matter what this is. You can actually throw this out. You can remove it. Similarly, you can remove that. You can make the resistance so large that it is infinity. You can basically pull this out. You can, if you want, you can make these wires, you can make it infinity. It doesn't matter. X and Y are irrelevant. It's very much like the regular Wheatstone's bridge, except for the regular Wheatstone's bridge, you don't have these in-between things. You have just 2 resistors joining up. There's only one bridge. Whereas here, you have 1 and second, and it doesn't matter as long as this ratio equal to this ratio equal to that ratio. Okay. So now you know that Wheatstone's condition or extended Wheatstone's condition is applicable to this circuit. So now I can remove these. And if I remove these, what happens? These 3 are in series. 2 plus 2 plus 2, right? Because these have been removed. So it's just 6. And these 3 are in series. 4 plus 4 plus 4. 4 into 3, 12. So actually, this whole circuit now becomes this. Very nice and simple. So you have 2 plus 2 plus 2, 6 ohms. And then here you have 4 plus 4 plus 4, 12 ohms. I don't care what is I1 and I2. That's not the question. The question is, what is I? So I need this current. But what is this? This is 12 volts. But these 2 resistors are in parallel. So what is the equivalent resistance? R1, R2 by R1 plus R2. 6 into 12 by 6 plus 12. 6 plus 12 is 18. So if I cancel this, that's going to give me 3. 12 by 3 is 4. So this is 4 ohms. So that is R equivalent. So what is I? I is the potential drop divided by the resistance. So 12 volts by 4 ohms, which is 3 amperes. Finished. Nice and simple, right? So actually this can be solved very nicely by using the extended Wheatstone's theorem. Of course, I don't think that IIT JEE was expecting you to solve like this. They probably expected you to solve using symmetry, but that meant you have to do a little bit of work to write down 3 equations, which is not bad. You can do it. It definitely is better than not using symmetry because then it will have a lot more equations. But if you use the extended Wheatstone's theorem, it is one step. Basically, you say, okay, 2, 2, 2, 6, 12, 6 into 12 by 18, 4 ohms. So this whole thing is equivalent to 4. So 12 by 4. Therefore, the current must be 3 amperes. So I hope you have understood this solution. If you like this video, please hit the subscribe button below. And if you have some comments or if you have doubts in physics or math, please write it in the comment section. I will take one of your questions and make my next video. See you all in the next video soon.